Hey guys, welcome back. 3.2 Measures of Variation is what we're going to cover today. If you remember from 3.1 describing central tendency, we learned mean, median, and mode. And those were in fact ways to describe the central tendency of the data. Mean being the expected value or the average of the data. Median being the middlemost point of the data. Remember, if we had an odd number of data, then there was actually one piece of data that would be our middle point. If we had an even number, there would be two pieces of data, and then we would average them. And then the mode, which is just the most common value of the data. So those are perfectly legitimate, perfectly reasonable ways to describe a data set, but they are, in fact, inadequate, and we'll see why here in a second. Right now we're looking at two data distributions, both for repair times of like auto repair for cars, I guess. We have the American Service Center, the National Service Center. These distributions have the same mean, median, and mode. But we can tell just by looking at the graph that they're vastly different. One of the ways that I would, I guess, logically or I guess non-mathematically interpret this, if we look at the American Service Center, the repair time, you're going to have a mean of 4 days. You're going to have a mean of 4 days, a median of 4 days, and then a mode of 4 days. But you know that every single piece of data is between 3 and 5. Okay, so it's a very skinny distribution. Now the National Service Center also has a mean, median, and mode of 4 days, but you can see that it has like a different level of dispersion. So it's interesting because these have the exact same mean, median, and mode, but clearly very different distributions. So we need to learn some tools to be able to describe these statistically, numerically, as such. So we have three different tools that we use. There's range, which this is just the largest measurement or the largest data point minus the smallest data point. So we can see now for the range for this would be 5 minus 3, so 2 from here to here. And then the range for this would be 7 minus 1. So that's the range that the data falls in. Okay, so that's our first way to describe the variation of the data or the dispersion of the data. Okay, so the next thing we have is variance, and that's just the average of the squared deviations of all of the population measurements from the population mean. That also holds true for a sample, we'll see as well. So not just population in there, it would be sample measurements from the sample mean. And then the standard deviation is just going to be the square root of whichever variance you have. So whether it's a population or a sample. But the standard deviation is just going to be the exact calculation of variance and then slap a square root on it. And that's what you have. That's how you have the standard deviation. So here we have the variance formulas. We have the variance for population and the variance for a sample. These are very similar formulas. This one's going to read sigma squared, so that term is sigma squared, and that is equal to the summation from I equal 1 to big N of x sub I minus mu all squared all over big N. Okay, and that is essentially each piece of data minus the mean squared all over n. So you're summing up each piece of data minus the mean, so the difference between a piece of data and the mean, squaring that, adding all of those up, and then taking it over the number of pieces of data, and that's what's going to give you the variance. The only thing that's different about the sample version of the variance is that n is going to be the sample size, not the population size, and well, it's s squared, so s squared, that's just pronounced s squared, it's not sigma squared. And we don't use the population mean, we use the sample mean, which which is denoted by x bar. There we go. Sometimes this pen is funky, but the formula is exactly the same. It's the piece of data minus the sample mean squared, so the difference between the piece of data and the sample mean squared, add all of those up and take it divided by n minus 1. Okay, so the population is just going to be big N, the sample is going to be little n minus 1. So those are the formulas for variance, and now we're going to hop on over to the worksheet and answer some questions about variance. Okay, guys. So 3.2 measures of variation. Calculate the range, variance, and standard deviation for the data set in 1A. So if you flip back over a page, you'll see that the data set in 1A, and I'm just going to order these right now, is 30.1, 30.8, 31.6, 31.7, and 32.1. So fairly straightforward to calculate the range. So we'll say range is equal to max minus min, and our maximum value is 32.1. So 32.1 minus 30.1 equal to 2. So you see that the range is 2. Now we need to calculate the variance. Well, we first need to know what is our mean, and is our mean a mu or an x bar? Well, our mean is going to be an x bar because this is a sample, right? So x bar is equal to, let's see what we calculated it as last time. It looks like 31.26. So now we would just run through the formula for, not sigma squared. There. We would run through the formula, and our formula is going to be s squared is equal to the summation from n equal 1 to big, or I guess little n, which is 5, of x sub I minus x bar all over n minus 1. Oh, that's squared. So we can say 30.1 minus 31.26 squared plus 30.8 minus 31.26 squared plus 31.6 minus 31.26 squared plus and that whole thing is all over n minus 1, which is 5 minus 1, or 4. Okay? And I'm going to get us some more room here. Uh-oh. There. More room to work. And we will see. So we already did the range. Now we're doing the standard deviation, and this is all going to shake out to be equal to, if you did the math, and I'm not going to show like the arithmetic on here, but I've checked it. So 2.572 all over 4. is equal to 0.643 approximately. And so that's equal to our S squared. And then we want to actually know the standard deviation too. So this is equal to our sample variance. But we want to know what is sample standard deviation as well. So sample standard dev is equal to just S, right? And so we know S is equal to the square root of S squared. So then we can say that's equal to the square root of 0.643, which is equal to 0.802. So that is sigma, or sorry, that is S. Okay, so that's how we do that. So let's move on to B, and I'm going to show you guys how to do B in Excel. So B is calculate the range variance, and standard deviation for the data set in 1B. 1B, if you turn back the page, which I am doing as well, is going to be looking at that whole data set of all of the car mileages. So I am going to look at this. Uh-oh, you guys can't see that, can you? So let me move that over. We're going to look at this whole data set, and we are going to calculate the range, the variance, and the standard deviation. So the first thing we can do is I will I'll sort this data from smallest to largest, and then we can see what the smallest value and the largest value is. So it looks like the smallest is going to be 29.8, largest is going to be 33.3, and we can say this minus this is equal to that. Okay, that's one way to do it. We can also use functions. We can say, if we don't just trust ourselves and don't want to eyeball it, say we have a data set that's enormous. So we say min, and that's going to return us the smallest value. Okay, min 29.8. Here, I will move that right here. And max. Okay, so we have a little Excel lesson here too. So it looks like we were right. So then we would just say that minus that. And we're going to check our work in a third way. I mean, we know we're right, but we're going to check our work with Megastat here in a second too. So that's the range. So we know that is the range. What else do we want to do? We want to do variance and we want to do standard deviation. So I'll show you guys kind of the by hand method of doing it. Okay, so we can say that these are the x sub i's. So we'll say then x sub I minus x bar or mu. Okay, so first of all we want to know what x bar is. So what is x bar? Sorry, x bar is not mu. X bar, or the mean, I should say. X bar we know is the average, which we learned how to compute last time. So the average is 31.56. So this is, I think we're still considering this a sample, because if you look at the graph, it actually does say sample of 50 on there. So just note that when we're calculating this. So we have an x bar of 31.56. We just want to get the differences between those. And so we'll say this, so equal the cell next to it minus this cell. And we want to lock that cell in. So we press F4 and that locks it in. Okay, enter. And we run it on all of the data. So those are the deviations. So then we'll say xi minus x bar, and we want to square all that. So this is going to be our column for that. So we just say this information squared. Okay, so then those are all the squared deviations. Now we want to know the sum of that, right? So the sum of those squared deviations, you go down and we have 31.18. And so then in order to determine what the variance is, we say, well, how many pieces of data do we have? We happen to know that it's 50, but here I'll show you a way to calculate that in Excel as well. So we'd say count all the data, 50. Okay, and so the next thing we do is we say the sum of the squared deviations divided by the count, and since it's a sample, we're going to use 1 minus that count, right? So we're actually going to be minusing it, or we're going to be dividing it by 49, not 50. So we get 0.63327 as our variance. And then in order to find the standard deviation, we would go ahead and take the square root of that. So the function is sqrt, open parenthesis, that number, we get that. Let's see if we're right. So there's also just, so that would be like the by hand way of doing it. You could also just say variance of, so var, the function var dot s, open parenthesis, on the data. Boom, we are correct. And then stdev for a sample on the data set as well. We're also correct. So that checks out. So now we've calculated, we've kind of done it a by hand method for range and for the standard deviation and the variance. And now we're going to use Megastat. So let me show you guys how to do that. Move this. So we go up to add-ins, which if you've installed Megastat and you've put it in the add-ins tab, it's going to be in add-ins. Megastat, descriptive statistics, and then you're going to be putting in the portion of the sheet that the data is in. And what do we want to know? We want to know the sample variance, sample standard deviation, and the range. So it looks like that is contained in this and this. So we hit OK. It'll run it into an output sheet. And sample standard deviation and variance. Let's see if we are correct. And range. Well, we will just pull these over. Our count was right, obviously. And sample standard deviation. Yep. This is the rounded version. Ours was not. Sample variance. This is rounded. Ours was not. Minimum and maximum we had up here. 33.3, 29.8, and range. 3.5. So that's how you do it in Megastat. So yes, I understand that it's definitely a lot easier just to click a button or put an Excel function in, but I did want to show you guys how it was done. So I wanted to show you by hand on the worksheet, then kind of by hand in Excel, then using the Excel function, and then also using Megastat. So this kind of stuff will come in handy. Feel free to use any Excel function or any way of doing it on the homework. You have all these tools at your disposal, so go ahead and use them. And hopefully me showing you guys this stuff in Excel helps, because I like to use Excel a lot, and I think it's pretty valuable. So and is that? No, we have one more problem to get to in our exercises, so we'll go ahead and do that as well. So if you guys turn back to so we just covered 3B, and we'll just say in Excel. And let me move this over. Calculate the range, variance, and standard deviation for the data set in number 2. So I'll just write down here what that data set is. You guys can turn back the page. 10, 10, 12. So the first thing I will write down is what our mean was. That was 9.6. We knew that from the last problem. And then what our n is. Oh, and this is a big N. We're considering this a population. So the range, we basically just find the smallest number, 6, the largest number, 12. So we can see range equals 12 minus 6, 6. Okay, so the range is the really easy one. Now variance we're going to do. So variance is now sigma squared. That's going to be the summation from I equals 1, so the first iteration, to n, which n is 10, because we have 10 pieces of data, of x sub I, it's an I, minus mu now. Oh, so did I write that wrong? I did, of course. Mu. So those deviations squared all over n, not n minus 1. And yeah, so then I guess we'll say 9 minus 9.6 squared plus 8 minus 9.6 plus 10 minus 9.6. Those should all be squared. All the way on down the line, all over 10. And that's going to end up being 32.4 all over 10 equals 3.24 equals our sigma squared. And then if we want to know standard deviation, so that was variance. Standard deviation is equal to just sigma. So sigma is equal to the square root of sigma squared, and that's equal to the square root of 3.24, which is equal to, looks like I just shortened it to 1.8 roughly. Okay, and then let's just go check our work in Excel. So I think I said dataset 2. Sure, we'll move over, and I will just, I guess I'll just say mean, and that will be average of this data, 9.6, that's what we had. I'll make a couple of columns here. Steal this. So I'll minus off the mean. Want to lock that cell in because we're going to be using only that. Okay, and then we're going to square those deviations. Ah! There we go. Add those up using the sum function. 32.4, that's what we got. Just make sure we counted correctly. So this will be what, I'll just say, what is n? That will be the count of this data. Right? So perfect. So then we know that the variance is going to be this, divided by this, which is 3.2, and then the standard deviation. So that's variance. that. Oh, that's going to be the square root of that. So 1.8. And yeah, I guess let's just check ourselves in Excel. So we'll go ahead and we'll say variance of a population, so var.p of the data set. Boom, that's right. And standard and equals standard deviation dot p of the data set. That's also correct. And now let's just check it in Megastat again. So I go up to Megastat, descriptive statistics, and not sample variance now, right? We got to go over to population variance. So let's just do that. Okay. Oh, I forgot to define a range. So 3.24 and 1.8. So we were dead on. So perfect in both accounts. So yeah, so we were in fact dead on in our calculations. So that's great. So now we're going to move back to the PowerPoint, and we're going to cover a couple of like supplementary topics that I guess are going to be a little bit less important at this point in the course, but you still might need to know. So I'm going to cover them fairly quickly. Okay. So we just covered population standard deviation. Now we're going to go into the empirical rule. And I should get my screen looking right. Okay, so the empirical rule just states for a graph or for a data set that is like evenly distributed, or I shouldn't say evenly distributed, a data set that is either normal or mound shape, and it's not terribly skewed to one direction or another direction. This, I guess, estimatingly, if that's a word, maybe not. Let's just say it tends to hold true, okay? And that is that between one standard deviation away from the mean, so right here we have mu, if you can see that, mu minus sigma, so that's mu minus one standard deviation, and then mu plus one standard deviation. 68.26% of the data are going to lie with there. Okay, so, and then now within two standard deviations of the mean, so mu minus 2 sigma and mu plus 2 sigma, 95%, 95.44% is going to be within there, be within that range. And then furthermore, plus or minus 3 sigmas, so mu plus 3 sigma or mu minus 3 sigma is going to encase 99.73% of the data. And so this is going to be, you know, something that we refer to as like the 68, 95, 99.75 rule, or the empirical rule. Okay, and this kind of helps you with knowing when a piece of data is like out of line. If something is more than 3 standard deviations away from the mean, there's a good chance that it might be considered like an outlier, a piece of data that like that typically shouldn't be in that data set, or that is misbehaving from the typical way that the data should be within that data set. So like if we were to cycle back and look at those repair times that we had looked at the beginning of the video, I think the American Service Center was between 3 and 5 the whole time. Well, if you took your car to the American Service Center and it took, 25 days, that would be considered an outlier. And that would certainly be something that is not within 3 standard deviations of the mean. Okay, so that's the empirical rule, or 68, 95, 99.75, or 73, I guess. The next thing we want to look at is a concept called z-scores. And I'll just read off this definition. For any x in a population or sample, the associated z-score is z equal to x minus the mean over the standard deviation. The z-score is the number of standard deviations that x is away from the mean. So yeah, so think of this fraction in 2 different pieces. So think of the top. The top is going to be x, which is the piece of data, minus the mean. Okay, so x is essentially the difference in the from the piece of data and the mean. So it's just the difference. Okay, and then the bottom is the standard deviation. So you're putting that difference in terms of standard deviations. So if you have something that's above it, so we can see it says a positive z-score is above the mean. That should be intuitive. And a negative z-score is below the mean. So I'll just show, like, we have like a normal-ish curve. It's supposed to be normal. We have mu right there, or x bar, it doesn't really matter. And we have a piece of data, say x, right here. Okay? We know that this area right here is going to be x minus mu. And then we can determine, like, that's the difference on an absolute scale, but we want to know what the difference is in terms of, like, how much does it typically differ from the mean. So then that's why we would say x minus mu over the standard deviation. Because the standard deviation is saying, hey, this is how much it should differ on a regular basis. So this is giving us that information. And yeah, so positive is going to be above the mean, negative is going to be below the mean, and if it's at the mean, it's going to have a z-score of 0, because essentially it's going to be mu minus mu, which is 0 over sigma. So 0 over sigma, just going to be 0. Okay, this is a concept that we're going to use a lot in Chapter 6, but right now I just want you to kind of understand where we're coming from with it. But we're not going to have a lot of calculations on it right now. But it's something that we are going to use heavily in the rest of the chapter. Then we have coefficient of variation. This measures the size of the standard deviation relative to the size of the mean. So this is essentially going to be giving us, like, how big is the standard deviation as a percentage of the mean. That's literally what it's going to give us. So you just take the standard deviation over the mean and then times it by 100. So relative to the size of the mean, how big is the standard deviation? And so that's our formula there. Coefficient of variation is equal to standard deviation over the mean times 100. And as you can see, used to measure risk, compare the variability of values about the mean, compare variability of populations or samples with different means and standard deviations. And so we'll look at those calculations in the review. Okay, outliers. Outliers are measurements that are very different from other measurements. They are either much larger or much smaller than most of the other measurements. And obviously that's very subjective in nature. And it's subjective in how you'd like to define them. A rule of thumb, if you need one, is anything above or below 3 standard deviations away from the mean, you can consider an outlier, or you can make a case that it's an outlier. But that's not exactly a hard and fast rule, but that is one way that you can kind of back up your claim that something is an outlier. Okay, guys, so that concludes Chapter 3.2. Hopefully you guys got a lot out of that. Feel free to, if I wasn't clear on anything, feel free to ask questions in the discussion tab, or email me if need be. But yeah, I'd prefer anything in the discussion tab, because then your question can be answered essentially in front of the class, so that somebody else who's having the same issue can get their question answered as well. So yeah, don't be shy about asking questions. I know we're actually getting into part of the material that's a little bit more difficult. So yeah, now's the time to ask them, because I don't want you guys to fall behind. And yeah, so that is our lecture for 3.2, and coming up soon is the review. All right, thanks so much, guys. Tune in next time. Bye.